Hi, in this video we're going to be talking about fields. So a field is a mathematical object which is defined by a bunch of axioms. Okay? These axioms are going to be properties that the field has, and every other property that the field has is going to be derived from these axioms. Okay? So this is a generic field, so I'm going to call this generic field F, but you should keep in mind some fundamental examples, Q and R. Now specific fields might have more properties than the generic field F, but we're going to be looking at specifically the properties that we can get from just the fact that something is a field. Okay, so what does it mean to be a field? Well, a field is a set with two binary operations. So a binary operation is something that has two inputs and it gives you one output. And to say that there's a binary operation on the set means that you can take, we'll say plus is the name of the operation. You can take two inputs, put them on either side of this, and the output is another element of the set. So for all A and B in the field, A plus B is another element of the field. Okay, so that's one of our binary operations. The other binary operation is multiplication, which we just write with a little dot. Okay, so whenever you have two elements of your field, you can add them together to get another element of your field. And whenever you have two elements of your field, you can multiply them together to get another element of your field. Okay, so now we're going to use these two binary operations, and we're going to just think about them as addition and multiplication. We're going to call them addition and multiplication. They are addition and multiplication. Okay, so this first statement here, AC, the A stands for addition, similar to the rest of these A's here. There's 4 addition axioms. And the C stands for commutativity. So this first axiom is the commutativity of addition, or addition's commutativity. And it states that whenever we have two elements of the field, adding them together in this order is the same thing as adding them together in the opposite order. Okay? So addition is commutative. You can switch the place of two elements that are added together. Okay? The next axiom is associativity. So addition's associativity. Addition is an associative binary operation on F. It says for any triple of elements of the set, you can associate them this way by first adding x and y together, and then after you're done with that, adding z. Or you could first add the last two numbers together, so y plus z, and then add to that x on the left. And you should get the same thing. These two are equal to each other. Okay, so hopefully that property looks fairly familiar. You've used it whenever you're using addition, just inherently. So oftentimes this property allows us to be lazy and just write something like A plus B plus C. Okay? So addition is only defined for two things. So if we want to add three things together, we need it to be associative for this even to make sense. Right? The definition of this is A plus B plus C, or A plus B plus C. And if these two were not the same thing, then we wouldn't want to use this notation. Right? We'd want to put the parentheses in there to say which one we mean, if it mattered. Okay? But for any field, it does not matter. Where you put the parentheses is not going to be relevant. Okay, the next axiom that we have is AID, the axiom of having an additive identity. Okay? So what this says is there exists some special element of our field, so that whenever we have another element of our field, we can add it to this element, this special element, and get the same thing back. So this element is called 0, and it's exactly what you would want 0 to be. 0 is the special number in any field where if you add 0 to something, it doesn't change the something, so you get the something back. X plus 0 is equal to x. And it does not matter what x is. So notice the order of the quantifiers here. So this is saying we're going to start out with this 0. In other words, we don't have to start out with the special x here. There'll be some other statements, like this next one here, that starts out with given an x, then there exists something. And this is saying something very different. There exists this something, and it doesn't even matter what the x is that we're going to pick. This something is special all on its own. And then once we have this, we can now look at any other element, and this equation will still work. Okay, so let's look at this contrast here with this next axiom. AIN, that stands for addition's inverse. Okay, so every field, or every element of every field, should have additive inverses. So additive inverses. And what that's saying is, you take any element of your field, there must exist this thing which I'm going to call negative x. So if x is the element of the field, then there must exist some opposite element, negative x, in the field, so that x plus negative x is equal to 0. So hopefully this seems intuitive. You can just stick a negative sign in front of whatever number you want, say in R or Q, and it makes sense, right? If the number was positive before, it'll become negative. If the number was negative, it'll become positive. But inherently, we don't have any notion of positive or negative in a field, right? In R or Q, those have extra structure, and we can work out some sort of notion for what it means for something to be positive and what it means for something to be negative based on whether it's greater than 0 or less than 0. And we'll talk about some order axioms later. But for now, we just have a generic field, and there's no special positive negative property that any of the elements would have. Okay? So when we write negative x here, this is just notation. So this is the name of some other element that has this property, and this axiom says that that element must exist. So for each one of these elements, it has a partner that when you add something together with its partner, you get to the additive identity. Notice that this right here, this 0, is the same 0 that this axiom asserts the existence of. So it doesn't even make sense to state this axiom because it uses 0 unless we already know that 0 must exist. Okay, so those are the axioms for addition, and now we have very similar axioms for multiplication. Okay, so to start out with, for any x and y in the field, x times y is equal to y times x. That's the commutativity of multiplication. Okay, so it's very similar to this, except we're using multiplication instead of addition. And same thing goes for associativity, MA. For any triple of elements of the field, you can multiply them with parentheses like this, and that's the same thing as multiplying together with parentheses like this. And the same thing goes for this. A times B times C, that notation only makes sense because whether you define it like this or you define it like this, you get the same thing. And so it doesn't matter which way you define it, which means we can just write it like this without parentheses. The next axiom we have is a multiplicative identity. So what this says is there exists some special number we call 1 in the field, and we have to also specify that 1 is not equal to 0, and that's what this notation is saying. So this is set subtraction. I'm taking the set of elements of f, and I'm getting rid of the set containing the 0 element. That's the same as this 0 up here. So I know 0 is an element of f, and so this set right here, written like this, is a set of all elements of f minus the 0 element. So I'm not including 0, and I'm saying 1 is an element of this set. In other words, 1 is an element of f, and 1 is not equal to 0. That's all that's saying. Okay? And I want this 1 to have this property that for any x in f, x times 1 is equal to x. Okay? So it might be strange to look at this requirement and say, why are we requiring 1 to not be 0? Because this equation looks like it should require 1 to not be 0. If I have x times, suppose I put 0 there, x times 0, and it always gave me x back, well, that wouldn't make any sense, right? This should be true for all x. Right? This is a for all x statement. So for all x in f, suppose this 1 was 0, and we'll look at what goes wrong here. Oops, should be an x. So what would go wrong if this happened? So if x times 0 always equaled x, then, well, there are certain things we want to have true here. And one of the things is that x times 0 will end up having to equal 0, no matter what x is. So if we define it to always equal x, that will mean that x will have to be 0. But this should be true for all x in f. And it turns out that's not a problem if our field only has one element in it. Okay? If that one element is the 0 element, then that one element is also the 1 element, right? And this requirement is just saying that those two elements have to be different. In other words, a field has to have at least 2 elements. Okay? So this thing looks funny, and we're going to avoid it. And it's just, it would make a lot of sense for most things that we use fields for a field to have 1 element, but not all things. There are some things that we really want 0 and 1 to not be the same element. So every field is going to have at least 2 elements, 0 and 1. They can't be equal to each other. Okay, our next axiom is multiplicative inverses. So we have this 1 defined now, so now we can talk about what it means to multiply a number by its multiplicative inverse and get 1. And notice this is very similarly quantified to this up here, the additive inverses. We start out with an arbitrary non-zero element. You're not allowed to invert 0. And we say that element has an inverse, and we call it x inverse, or x to the power negative 1. And it's an element of the field, and it has this property that x times x inverse is equal to 1. Okay? 0 does not have this property. There is no 0 inverse, and that's perfectly fine. We don't want fields to have 0 have an inverse in general. But again, you can just picture these very standard examples. R and Q, those have a 0 element which is not multiplicatively invertible. And things would sort of break if we tried to divide by 0, and we just don't want that. Okay, so we have the addition axioms, we just did the multiplication axioms, and there's one more axiom that combines the two together. D is for distributivity. So this is the distributive property, and it says whenever you have a triple of numbers x, y, z in the field, then x times y plus z, you can distribute this in, and you're going to get x times y plus x times z. Okay? Oftentimes when you see the distributive property in math, you'll see it as a left distributive property and then a right distributive property. The right distributive property would say something like this. You have y plus z times x, and you'd say this is equal to y times x plus z times x. Okay. The reason we don't need this extra equation here, the right form of this distributive property, is because multiplication is commutative. So writing this is the same thing as writing this. And similarly, writing this is the same thing as writing this. Okay? Because you can switch this multiplication, and similarly you can switch each of these individual multiplications. Okay? And in general, one of the properties that we want a set of axioms to have is there's nothing extra in there. There's nothing that we can take out and have it still completely describe the object that we're trying to describe. So we don't want to include anything superfluous. Okay, so this in its entirety, it's going to tell us a lot about the object f. Okay? In particular, we're going to be able to prove some things using just these 9 statements here. And they might seem obvious, but the proof isn't. It's obvious, duh, shaded box. The proof should involve some logical reasoning that starts from these axioms and gets to where you want to be. So this first statement here, proposition 1, is that the additive identity is unique. Okay? So there's nothing about this statement right here that says the additive identity exists, that says there can't be more than one of them. Okay? So what does it mean for there to be more than one of them? Well, I'm going to start the proof here. So suppose we have 2 of them. So I've named the first one 0, and I've named the second one, this imposter, I've named it 0 prime. Okay? And the goal here is to say why there can't exist another one, 0 prime. But the way we're going to phrase this is we're just going to suppose we have 2 of them. We're not going to assume that they're different, and we're going to eventually show that they are equal to each other. Okay? So we want to show that 0 is equal to 0 prime, therefore there can be only one. Okay? Or another way to say that is if you have 2, then those 2 are actually the same. Okay? So now I'm just going to write down the definitions here. So what it means to have 2 different, or just 2 additive inverses, it means we have this property for each of them. So we're saying it exists, so that part's already done. So we want to have this property that for any x in f, x plus this 0 or 0 prime is equal to x. Okay, so far I've just written down the definitions and the setup here. So we have 2 different zeros, 2 potentially different zeros. We're eventually going to want to show that they're equal to each other. And for now, we've just written down what it means for them to both be zeros, for them both to be additive identities. So we have these 2 equations we can work with, and those 2 equations should work for every single x in the field. So we want to take advantage of this. We're going to exploit the fact that we can plug in whatever x we want. And the way we're going to do that is so I'm going to take this equation right here. And I'm going to say let's let x be this other 0. So we're focused on this equation right here. This does not have a 0 prime in it. So I'm going to let x be this other 0, 0 prime. So then x plus 0 should have to equal x. Okay? So that's coming directly from this right here. Okay? Remember, it has to work for every x in the field. Right? For every x in the field, this equation is true, and I'm saying let's look at this one specific one, and it should work there because that is an element of the field. Okay. So we know that 0 prime plus 0 is equal to 0 prime. Well, we can do the same thing for this other one, and get a very similar equation that looks slightly different. Okay, so now I'm going to let x be the normal 0, the original 0, and use this equation with the 0 prime in it. And that's going to tell us that 0 plus 0 prime is equal to 0. So x plus 0 prime is equal to 0. Or sorry, x plus 0 prime is equal to x, where x is equal to 0. Okay? So what do we notice about these two equations that we now have? Well, the left side of them looks very similar. And we're trying to show that their corresponding right sides should be equal to each other. That's our goal. And how do we get from here to here? Why do we know that these two things are equal? Well, that's one of our axioms. Okay? So one of our axioms says that you can switch the order of addition. So in other words, you have commutativity of addition. So I'm just going to write this in one long line. Okay. So this statement right here, this equality, is coming from this right here. Let me just circle that in green. Okay, the fact that 0 is equal to 0 plus 0 prime is coming from that statement. And finally, this last equation right here is coming from our first axiom, the commutativity of addition. Okay, and putting this all together, along with some basic property of equality that we want to have true always, whenever we talk about something being equal to something else. So this is a property that sets have in general, so it's not a special property that we want to talk about for fields, because it's going to be true for any set, and every field is also a set. So one of the properties that the equality has is if this thing is equal to this thing, and this thing is equal to this thing, then the first thing is equal to the third thing. And you can also chain together 4 of them like we have here, and because each one is equal to the next one, then the first thing must be equal to the last thing. Okay? So we now have that 0 is equal to 0 prime. Okay? So I'll just say okay, 0 is equal to 0 prime, or 0 prime is equal to 0, which means we only have one additive identity. In other words, if we have multiple additive identities, then they're actually the same. So this next proposition here, proposition 2, is something that I've already mentioned. It's this nice property that we want to have, but it's not one of the axioms that's given to us. So it's this property that for any x, x times 0 should equal 0. Okay? Well, why does this work? Well, it's going to have something to do with these things defining 0 and possibly this property right here that 0 has to have. Okay? So let's just start experimenting with some stuff, and hopefully we'll end up with some sort of reasoning. And this is almost certainly better done before you watch me do it. So I suggest you pause the video and try to work this out yourself. Try to justify why starting with an arbitrary x and multiplying it by 0 should give you 0. So for me, there's not much exploration because I already know how to do this. So I'm going to try to mimic this exploration process, but it's going to be very short, and I'm sorry. So I'm just going to write down some scratch work, and then we'll start the proof afterwards. We don't know what x is. We can, if we want, we can plug in whatever x we feel like there. So we can choose the value of x. And we want it to have this nice property, x times 0 has got to be equal to 0. So we want to write 0 in a nice way. For example, one of the ways we could write 0 is something plus its opposite. Okay. So one of the things we might want to do is write this 0 as something plus something. Okay, so we don't want to, for example, use x here. So this would be a true statement. I just replaced 0 with x plus the opposite of x. X plus the opposite of x is 0, so that's fine. But this is not going to lead us in a good direction because it's going to be x squared plus x times the opposite of x. And we don't have any way to get a handle on what that should be. Okay? So instead of picking x here, I want to pick a special number that we have in the field. Okay? So there's two special numbers. There's 0 and there's 1. And let's just look at 1 real fast. Okay? We have 1 plus negative 1. And this is going to tell us that, so we have x times 1, and then x times this opposite of 1, this negative 1. And again, there's not much we can do with x times negative 1 at this point because we don't know what that should be. Okay, let's try our other special number. Zero. Okay, so I have here the opposite of 0. And so if I knew what that was, this might be very easy. So one of the sort of first steps in this is to figure out what negative 0 is. So negative 1 wasn't something we can figure out what that is because it is just negative 1. But negative 0, you should have some intuition from thinking about our two standard fields here, Q or R, that negative 0 should just be 0. Okay? So that's a good first step. We want to try to show that negative 0 is 0. And once we had that, then this statement right here would be x times 0 on the left. And on the right, we could use our distributive property, right? It looks exactly like x times parentheses with an addition. We can distribute the x in. And as long as we knew that this negative 0 was 0, then this statement is almost exactly what we want. Okay? So we'd want to somehow get from here to the statement that 0 is equal to x times 0. And maybe you see how to do that, maybe you don't. One of the things that we're not allowed to do, because subtraction isn't defined, is we're not allowed to just subtract x0 off of each side of the equation and get from here to here. But there is some way to get from here to here, and essentially it's the same thing as subtraction, but we're not allowed to use subtraction as an operation. Okay? We only have addition and multiplication. So, we need to do two things. We need to figure out why the opposite of 0 is 0, and we need to figure out how to get from here to here. So again, if you're watching this and you haven't figured this out, you should pause the video here and try to figure out those two things. Okay, so I'm going to start out with the second one and show how to get from here to here. And that's going to be done by adding something to both sides of the equation. So we are allowed to add two things, to add something to both sides of the equation. Okay, so what does this mean? Or what do I want to add to both sides of the equation? Well, I want to cancel out one of these x times zeros. And x times 0, whatever it is, it's an element of the field. And therefore it has an opposite. Okay? So I'm going to take this. So this was a question mark here. I'm going to take this and I'm going to add on the opposite. I'm going to sort of write this in a strange way. Too many parentheses. Just because it is notation. Right? I wrote my existence of negative x in parentheses. So I'm doing the same thing here. The whole thing is in parentheses. And that's convenient because we don't want to have plus and minus. We don't want to have those two operations right next to each other. Or we don't want to have those two symbols right next to each other, I should say. It doesn't make sense to say plus minus this. What we really want to write is subtraction. But because that's not defined, we're going to say plus opposite of this. And that involves a negative sign. And we're just going to put parentheses there to separate those two symbols. Okay, and this symbol right here, or these parentheses right here, these have to go around the x times 0 because it is one element that we are taking the opposite of. We're not taking the opposite of x and then multiplying by 0. We're taking the opposite of x times 0, whatever that happens to be. It doesn't really matter what it is. It turns out that that's 0, but that's what we're trying to show here, so we can't assume that. Okay, but it is an element of the field, and so it has an opposite, according to this axiom right here. And so we can add it to both sides of the equation. All right. So, what happens when we do this? Well, the whole point of adding the opposite of something to the original, x plus opposite of x, is you get 0 out of that. Okay? So this right here is 0. And this right here is 0. Okay? So 0 is equal to x times 0 plus 0. Okay, and that's almost exactly what we want. Now we just have to, so we're trying to get to this 0 is equal to x times 0. And we have this extra plus 0 on the end, but 0 is this special number that whenever you add it to some x, you always get the x. Okay? So this is going to tell us that 0 is equal to just x times 0. Okay? The plus 0 can just be left off. Okay. So the next thing we need to show is that the opposite of 0 is 0. So how might we go about doing that? So notice that whenever you add 0 to something, it doesn't change it. And there's a defining property for the opposite of 0. Right? The opposite of anything is defined by this equation right here. Okay, so there must exist this opposite of 0, so that when you add it to 0, you get 0. Okay, so I'm using x is equal to 0 here. And I've written these things in the opposite order, but that's okay because we have commutativity. Okay, so now I'm going to take this, and I'm going to use the fact that when you add 0 to something, like right here, you get the same thing back. Okay, so in other words, this plus 0, very similar to right here, can just go away. So the opposite of 0 is equal to 0, just like we want it to be. Okay, so we now have all of the pieces, and we're now ready to formulate the proof. So let's go ahead and do that. Okay, so it's convenient to start out with the fact that the opposite of 0 is 0. And to do this, I'm going to make a sort of a separate claim. So this will be sort of a subproof. So I'm going to call it claim 1. It turns out it'll be the only claim, but it's still fine to just number things. So claim 1 is that the opposite of 0 is equal to 0, or negative 0 is equal to 0. Okay, so notice there's nothing to quantify here. 0 is already quantified right here. There exists a 0. So I'm now going to have a proof within a proof, and I'm going to specify what this thing is proving. We're proving claim 1. Okay, so the reasoning was already stated, so I'm just going to write this down. So let's see, we're going to start out using this axiom here. So AIN is the name of the axiom. This should work for all x. So I'm specifying that we're using x is equal to 0. And this thing says there exists. The existence of it is already sort of implied by the fact that we're talking about it. And so I'm just going to jump to this equation right here. And say zero plus negative 0 is equal to 0. So now we're going to use this property right here, that when we add 0 to something, we get the same something back. But also our 0 is written on the left instead of the right, and so I'm just going to mention that we're using commutativity as well. So I'm using AID, the one that gives us this equation, which cancels out the plus 0. And so I want to specify which x I'm using here. And this x that I'm using is this non-zero thing, or it is 0, but not notationally. So x is equal to negative 0. Okay, so then by this, with that specific x value, we get this. So x plus 0 in the opposite order is equal to x again. So that's our x again. And now we can combine these two things. 0 plus negative 0 is equal to this, and 0 plus negative 0 is equal to that. Okay, so again, by chaining together equality, this is called the transitive property of equality. We're able to say that this is equal to that because they're both equal to this sum. Okay. I'm going to leave off my shaded box there. And maybe put this other symbol here, which is very similar to a shaded box. It also means that we're done with the proof. And now we're going to continue on with our main proof. Okay. So our main proof is the proof of this proposition. And we want to do the rest of the work that I erased down here. Okay? We want to write that in proof form. Okay, so we're going to have this reasoning. So by this property right here, we want to write this equation. Okay, so that's going to give us that is equal to 0. And so x times 0 is going to be equal to x times this other thing where I replace the 0 with this sum. Okay, so all I've done is I've replaced 0 by something equivalent to 0. And now I'm going to distribute in. Okay. Now I'm going to use the property that negative 0 is equal to 0 and replace this negative 0 with 0. Okay. So now we're going to add the opposite of x times 0 to both sides. And if I just wrote that down, it wouldn't really be clear what I'm doing, because what does both sides mean here? Well, both sides means the far left and the far right. So I'm just going to rewrite that. So I'm going to add this opposite of x times 0 to both sides of this equation. And that's going to give us and I want to be careful here. And I'm going to squeeze this down on the last line here. So we have this, and now this implies, because this is 0 and this is 0, that 0 is equal to x times 0. And the reasoning for that is this fact that x plus the opposite of x is 0, so AIN. And we're using that twice. We're using it once on the left side and then once on the right side. Okay, so that is the proof. And you might be a little unhappy with this, potentially, because it is not very efficient. So this may not look like a long proof to you, or it might look gigantic. Proofs in general can be pretty much any size. There are extremely high-level one-sentence proofs, and there are proofs of relatively simple statements that are thousands of pages long. Okay? So it's not easy to look at something and say, oh, that's too long or it's too short. But something you might not be happy with is there is some sort of inefficiency here. So this claim 1 that we have, this negative 0 equals 0, it's not actually necessary to have this in here. So it is nice to say that negative 0 is equal to 0. That's something we can prove from the axioms. And that in and of itself is a fine thing to prove. But we didn't really need it for this statement. So where did we use it? We used it right here. So we have 0 plus negative 0 is equal to this thing. And then, basically we wanted to say 0 is equal to 0 plus negative 0, and then have something to do with that. Okay? But we could have just as easily said 0 is equal to 0 plus 0. And we wouldn't have the negative there. And 0 is equal to 0 plus 0, because we're allowed to take this equation and plug 0 into it. We don't have to use this equation to get 0. We can do 0 plus 0 equals 0. So using this with x is equal to 0. Okay? And if we did that, we would have x times 0 equals x times 0 plus 0. And that would allow us to distribute it and get this step right away. We wouldn't have to know that negative 0 is 0. That being said, it's still nice to see this sub-proof of a claim within a proof. And in general, when you're writing a proof out, the first time you write it, you're not going to necessarily write it in the most efficient way. That doesn't mean it's not correct. Okay? And that happens a lot in mathematics. There are proofs of your famous statements, and then potentially many years later, somebody comes out with a nicer proof, or shorter proof, or simpler proof, and that is itself an accomplishment. Okay? Coming up with a simpler proof of something that's already known to be true. And that's just the way it is. Okay? So don't worry if your proof isn't as efficient as possible, as long as all the steps are there and it's correct. Alright, so that's the last proof I plan on writing out, but I still want to go over some of the proof ideas for some other statements that look like they should be really easy, but they do require some manipulation of the axioms in order to actually determine that they're true. Okay, so this statement here, for each x in f, negative x is equal to negative 1 times x. Okay, so this is a statement that we just take for granted as in R or Q, in our basic fields that we're using. This is sort of just true because we're used to it, right? And the same thing goes for this last proposition. X times 0 is equal to 0. We're just used to that. We've seen that since elementary school, and it's just hammered into our brains. But we want to say why this is true based on this small list of properties that a field should have. Okay, so this right here is a special number that we know must exist because 1 exists. So for each number, for each element of the field, there has to exist an opposite of it. Okay, It turns out we don't know too much about what -1 is, though. For example, in some fields, -1 is equal to 1. Okay? There's nothing restricting that. Right? There is actually a field, the same field I'm talking about. There's a field with just two elements, 0 and 1. It turns out that's all you need to make a field. There's also a field with 3 elements, 4 elements, 5 elements, not 6 elements though. Okay? We might talk about some fields later. But for now, you should keep these in mind. So intuitively this is true, and we want to say why. So the first step is to write down some property that this number right here has. Okay, so we're just talking about the main idea. We're not going to write out a formal proof. So the main property that -1 has is if you add it to 1, you get 0. Okay. Well, one thing we might want to do with this equation here is multiply both sides by x. Be a little bit careful here. So x times 1, I'll multiply on the right by x. So 1 times x instead of x times 1. Not that it matters. Just matching the format here. Okay. So, what do we know about this? Well, 0 times x, we just proved a proposition that x times 0 is equal to 0 for all x, and multiplication is commutative, so we can switch the order. This is still going to be 0. So that we can say is 0. Also, this 1 times x, well, 1 is the special number that when we multiply it by whatever, we get the whatever back. Okay? So 1 times x, or x times 1, is just going to be equal to x. So we don't have to write 1 times there. All right, so now what we have is x plus something, this thing which is -1 times x, is equal to 0. And so it satisfies this property right here, x plus the something is equal to 0. It satisfies this property that we want -x to have, but does that mean that this thing has to be equal to that? Well, not directly. We still have to do some work to get there. So just because it has this property doesn't mean it's the same thing, because there's nothing in here that says that this -x has to be unique to make this equation true. Okay? Remember, we proved that 0 itself was unique, so even this thing doesn't have uniqueness written into it. But it turns out this element, the opposite of x, will be unique. There's only one opposite of x for each x. Okay? But that's something that we have to work out for this particular example. So we want to do some algebra to both sides to say that this should actually be equal to the opposite of x. Okay? And one thing we can do is just add the opposite of x to both sides of this equation. Okay, so I'm going to copy down the equation, and I'm going to add the opposite of x to both sides. So I'm adding it to the right side here and the left side here, and I'm being lazy about which side is which because addition is commutative. Okay, so two nice things happen here. First thing is this right here, because there's an x on this side, adding the opposite of x to it is going to make that whole thing 0. Right? X plus the opposite of x in whatever order you want is going to be 0. And the other nice thing that happens is now we have 0 plus one thing is equal to 0 plus this other thing, and we want this one thing to equal the other thing, and we're only one step away because 0 plus something doesn't affect what the something is. So x plus 0 is equal to x. So this is going to, we can always cancel out a plus 0 and get negative 1 times x is equal to negative x. Okay, so again, I'm not going to write out the formal proof, but the main idea is here, and hopefully you can take this and turn it into a formal proof. Most of the ideas are literally just equations written down. And so the proof itself would be a lot of filler words like, therefore we have this, thus we have this, now we have this, etc. Okay, so that is that. Alright, proposition 4 here says that for each y in the field, if there exists an x so that x plus y is equal to x, in other words, that y, if there exists an x so that y is acting like 0 when added to x, then y must actually be 0. Okay? If it acts like 0, if it satisfies this equation for one value of x, then it must actually be 0. 0 is the only thing that satisfies this equation for any x, is another way of saying that. Okay? So I just want to point out the difference between this and this, and it has to do with the quantifier here. Okay? So we know that there's some y so that for every x this equation happens. That's exactly what this statement says. But there's nothing about this, the fact that it works for all x here, doesn't mean, and also we know that 0 is unique, so there's only one 0 in the field where this equation works for all x. But that doesn't mean there might not be something else that won't work for some particular x, right? This statement that there is an x here, this existential quantifier, is very different than this universal quantifier here. So just to note, we've already proved proposition 1 said this exact same statement, but where this quantifier was a for all, was a universal quantifier. Okay. So another way of saying this is proposition 0 said for each y in f, if for every x in f you have this equation, then y must be 0. Okay? So in other words, if you have some element y that looks like 0 for every element x, then y must be equal to 0. There is only one 0. So if you have another one that looks like 0 prime, then 0 prime is actually equal to 0. So that's proposition 1 that we already showed. And this is saying something a little bit looser. So it's saying it only has to satisfy this equation for one value of x. Okay? And that's a lot less strict than saying it has to work for all values of x. So without prior knowledge, there's no reason to believe that this y must be 0. Okay? But it turns out y does have to be 0. Okay? So I want to talk about the format of this proof. So I'm not going to write down the whole proof, but I do want to write down the beginning part where we quantify things. And we're proving this for each statement, or for all statement. And whenever we're doing that, we want to start out with an arbitrary value for that. So our arbitrary value is going to be obtained by saying let y be an element of f. Okay? So we want to prove this for every value of f, for every value y in f, and so we're letting y be this arbitrary value in f, and if we prove it for this y, well then it has to be true for all of the potential y's. Okay? It has to be true for every potential y in f. Okay? So the next thing we have to do, so that's the thing we've seen before, the next thing we have to do is use the fact that we're proving an if-then statement. Okay? So that's the next, that's the next step in this. So we have our arbitrary y, and then we have an if-then statement that we're trying to prove. So whenever we're proving an if-then statement, we need to assume the hypothesis and then show the conclusion. Okay? So the hypothesis itself is that there exists this there exists this x with this equation satisfied. Okay? So we need to assume that there exists this x. Okay, and then after you do that, after you state that you're assuming the hypothesis, you then want some sentence there stating your goal. So the goal for the rest of this proof is to show the conclusion, which is that y equals 0. Okay, so that is the start of the proof, and I'm not going to write out the rest of it. I would just want to talk about the scratch work that would lead you to believe that y should be equal to 0. Okay. So this is a good point for you to pause the video, try this out yourself. You've already seen a few examples of these things working out. So why does it work out in this case? Okay. All right, so we're looking at this equation right here. X plus y equals x. That is something we're assuming works out. So not only do we have this y that we're starting out with, we also have this x we have to assume exists so that this equation is satisfied. Okay, so we can work with x and y. In particular, x has an opposite. And while we can't subtract x from both sides, we can add its opposite to both sides, which is the same thing as subtraction. Or at least the idea is the same. And the result is the same. Okay, so you can take this equation and add the opposite of x to both sides. Okay, so here I want to say these two things cancel, but really what I mean is they turn into 0 when you add them together. And here the same thing. And then 0 plus y is the same thing as y, and that's going to give us y equals 0. Okay, so that is the idea behind that. And that's all I'm going to write for that. Okay, proposition 5 is a statement that looks, again, very simple, and we want to reason out why this should be true. So I shouldn't start out a sentence with a symbol, but I'm going to anyway out of laziness. That is my sentence right there. Notice there's no quantifiers here, there's no variables that we're using. We're making a statement about things that are already quantified in the axioms. So we know that there exists a 1, and we know that there exists an additive inverse for every element, so there has to exist this -1. We're allowed to multiply two things together, and again there exists a 1. Okay, so we have all of these things, and we can talk about what it means for these two things to be equal. So why is -1 times -1 equal to 1? So this is something you just have to sort of play around with, and you might try something like this. So remember, we have this defining equation for what it means to be -1, and that is this. If we add 1 to it, we'll get 0. Okay, so this is very similar to our proof of x times 0 equals 0. We're just taking something and writing it in a different way, and hopefully we get something out of this. Okay. The next thing I'm going to do is try to create this product in this equation by, say, multiplying both sides by -1. Okay, so a lot of nice things are going to happen here. In particular, I know once I distribute this in, that I'll have -1 times -1. And then a lot of these other things are going to be easy to compute. I know what 0 times something is. That's going to be 0. And I know what 1 times something is. That's going to be the something. Okay, so let's go ahead and distribute this in. and I should know what all the pieces are, and then I can just essentially solve for the piece that I want. Okay, so this is going to be negative 1 times 1, and this I'm just going to rewrite as 0. Okay, so I've distributed on the left side, and I've simplified the right side using proposition 2. And now we have this plus this is equal to 0. And what is negative 1 times 1? Well, according to this, it should be negative 1. Right? We're exactly using the multiplicative identity property where our x value is negative 1. Okay, so that's going to tell us that negative 1 times negative 1 plus this thing, which is negative 1, is equal to 0. And, well, we're only one, maybe 2 steps away. We just need to get rid of this. We need to get this to the other side in order to say what this is. And to do that, hopefully it's clear, we want to cancel this thing out, and the way to cancel it out on the left side is to add its opposite to both sides. So what is the opposite of negative 1? Well, it turns out it's positive 1. Okay? But I don't actually need to know that. I'm just going to add 1 to both sides. And even though this is technically the opposite of 1, and I haven't shown that the opposite of 1 is equal to 1 yet, I can still use the fact that 1 plus the opposite of 1 is equal to 0, and that's the only thing I need for this. So this is another case where we could be slightly inefficient, but I'm just choosing not to be, sort of, or I've noticed that I don't have to be inefficient. Okay. And this tells us that, so this is exactly what we want, negative 1 times negative 1. Okay. This is 0. I'm just going to leave that off. It is plus 0 though, and there is technically another step to get rid of that plus 0. And then here also we have a plus 0, so I'm just going to leave that off. Okay, and that's exactly what we were trying to show. So again, it's a statement that seems obvious just looking at it because you're just so used to these numbers multiplying together, but you really want to stop and think why. And these are the only tools you have to reason out why, along with things that you've proved before. So on the homework, there's going to be a few of these things to prove, and you're allowed to use any of these things along with any of the propositions we've shown in this video. Okay, that being said, there is one more proposition. Okay, and I guess I should quantify x here. Okay, so the opposite of x is x. So that thing that I said was true for 1, it's true for every x, right? If you take the opposite twice, you get back to the original. Okay, so why is this true? So yet again, you should pause the video and try to work this out on your own. So what is the thing that defines the opposite of something? Well, it's this equation right here. Okay, so I know that if I take this and add it to the opposite of x, I should get 0. Okay, so if I take this and add it to the opposite of x, I should get 0. Okay, so we have this equation that defines this opposite of the opposite of x. Okay, and very similar to some of these other ones, we're now going to manipulate that equation and try to solve for this and get something simplified down on the right side. And to do that, we want to get rid of this opposite of x. And one of the nice ways to get rid of the opposite of x is to add x to both sides of this equation. Okay, well, once we do that, this part's 0, so it's going to go away. That's 0 plus something, so that goes away. And I'm going to skip a couple steps here of canceling out some zeros. The opposite of x is just x. All right, thank you for watching.